Hello. Today we're going to talk about section 4.3. 4.3 contains derivative tests. We've been doing this for a while where we compute the derivative and see what the derivative tells us about the original function. I wrote this test on the board quite a while ago, I think maybe even during the first week. It's something called the increasing-decreasing test. We noticed it graphically, and it turns out that it's true. If f prime is positive on an interval, then the function itself is increasing on the interval. Likewise, if the derivative f prime is negative on the interval, then the function is decreasing on the interval. Thinking about this graphically, I think should easily convince ourselves that it's true. Right, here's the graph of a function, y equals f of x. To the left of this location, right here, all of my derivatives are positive. We can imagine that all of the slopes of the tangent lines to the left of this location are positive. And so, over here, f prime is greater than 0, the slopes are positive, and very clearly the function's going up, it's increasing. On the other hand, to the right of this location, all of my tangent lines seem to have negative slopes, which means that the derivative is negative, and again, very clearly the function is going down over here. So the function is decreasing. That's all the increasing-decreasing test tells me. In a moment, we'll do an example where we have a formula for the function, and we want to figure out the intervals where the function increases and where the function decreases. Knowing the increasing-decreasing test can also help me identify where a function has local maxes and local mins. And it's pretty easy to see. At this location, I have a local maximum, right? I have a value that's the largest of any of the nearby values. What we saw, let's call this this x value c here. And so at the top, right, I know that f prime of c is equal to 0, which means that c is a critical number. Okay, in the last section we defined critical numbers. And so if I look at numbers below the critical number c, my derivative is positive. To the right of c, the derivative is negative. And so at c, if I'm reading from left to right, the derivative changes sign from positive derivative to negative derivative. And of course, what I have at c is a local max. So that is part A of what's called the first derivative test. We're assuming that c is a critical number of a continuous function f, and here's what just happened. If my derivative f prime changes from positive to negative, so the function goes from increasing to decreasing, at the critical point, then the function has a local max. Likewise, if your derivative changes from negative to positive at the critical point, going from left to right, then the function will have a local minimum value at the critical point. The last option, of course, is that the derivative might not change sign at the critical point. And if that happens, then the function doesn't have a max, and it also doesn't have a min at that location. Before I do the example, I also want to talk a little bit more about concavity. We saw this before. Knowing if a function is increasing and decreasing can help me distinguish some functions. Right, this function is increasing, this function is decreasing, so obviously they're different functions. But what if I have an example like this? What if my function on the interval from, say, 2 to 5 is increasing and it looks like that? And then I'm going to have a similar curve similar function. Also on the interval 2 to 5. Maybe it'll have the same height at the endpoints, roughly. And it's still going to be increasing, so I can't use increasing and decreasing to differentiate between these two pictures. But this time, the function looks like this. So very clearly, these are different functions, right? But they're both increasing on the interval from 2 to 5. So what differentiates between these two images? Well, we might say that they're kind of curved in the opposite way, and they are. If we think about it a little bit more carefully, we might think about the slopes of the tangent lines. Okay, in either case, the slopes of the tangent lines are positive, but what's going on with the tangent lines? In this first picture, yes, my slopes are positive, but they seem to be getting more positive. In other words, the function is getting steeper as I go from left to right. And so here f prime is increasing. Right? The derivative is increasing. But the derivative is itself a function. And so if you have an increasing function, the derivative in other words, that would mean that its derivative, or the second derivative, is greater than 0. And that's what's going on in this picture. It has a positive second derivative. On the other hand, in this second picture, yes, my slopes are positive, but they're getting less positive. And so that means that the derivative f prime is decreasing. And of course, if we have a decreasing function, its derivative is negative. Well, the derivative of the derivative is the second derivative. So in this picture, the second derivative is negative. In the first picture, we say that the original function f is concave up. And I'm going to just abbreviate that CU. In the second picture, the curve is concave down, and I'm going to abbreviate that, f is CD. All right, concave up is right side up, and concave down is upside down. You might remember that. But very clearly, there's a relationship between the sign of the second derivative and the concavity of the original function. In particular, we have what's called the concavity test. And it has two parts. If f double prime of x is greater than 0 on an interval, then f, the original function, is concave up on the interval. The second part of the concavity test is probably what you expect. If the second derivative, f double prime of x, is less than 0 on an interval, then the function f is concave down on the interval. Let's do one example and see how this works out. All right, this is going to be 4.3, number 16. The function in this example is f of x equals 4x cubed minus 3x squared minus 18x plus 4. And I want to do a few things. I want to find the intervals of increase and decrease. Okay, so find intervals where f is increasing. I'm going to try to also find intervals where f is decreasing. That's the first part. For the second part, I'm going to locate any local max and local minimum values. And then the third thing we'll do in this example is we'll find the intervals of concavity. All right, so we'll determine where f is concave up and where f is concave down. Okay, to answer all of these questions, I need derivatives. All right, so we'll start with the first derivative. F prime of x is equal to 12x squared minus 6x minus 18. For my increasing decreasing test, right, where f is increasing, I need to know where the first derivative is positive. To figure out where f is decreasing, I need to know where the first derivative is negative. Well, to figure out where f prime is positive and where it's negative, I should figure out, first of all, where it equals 0. So I took the derivative, I set it equal to 0, and now I try to solve for x. Well, the first derivative is a quadratic, and this one's not so bad to factor. All three of my terms here have a 6 in common, so we can factor out a 6. That leaves us with 2x squared minus x minus 3. And then dividing both sides by 6, in other words, cancels the 6. This quadratic, inside the parentheses, we can factor. The first term here is 2x. The first term in the second parentheses is x. And then we're going to have 2x, minus 3, and then x plus 1 equals 0. Okay, you can check if you FOIL this that it works. When you have a product equal to 0, one of your two factors has to be 0, so you get 2x minus 3 equals 0, or x plus 1 equals 0. And so here you get 2x equals 3, or x equals 3 over 2. And the other option is that x equals minus 1. So these are my two critical numbers. Oops. In other words, these are numbers in the domain of the function where the derivative equals 0. When I solve a problem like this, I locate my critical numbers, and then I make a number line. I make a number line for the first derivative. Alright, so here's my real number line. I'm going to label it f prime. I want to stick the critical numbers on the number line in the right order. So here's -1, and here's 3/2. I see that these two critical numbers break the real line into 3 subintervals. At the critical numbers, f prime equals 0. But that's the only place where f prime equals 0. So on each of the 3 subintervals, the derivative has to either be positive or negative, but it can't change. And so if I want to figure out if the derivative is positive or negative on each of the intervals, all I have to do is pick a test number in each one of the intervals and plug it in to the derivative to determine the sign. So over here, when I'm less than -1, I'll probably pick the test number -2. In the middle interval here, I can pick x equals 0. And then in the rightmost subinterval, we can pick x equals 2 as the test numbers. I should plug the test numbers into f prime if I'm trying to find increase and decrease intervals. So, what's f prime of -2? Well, I have a formula for -2, and I can plug I have a formula for f prime, and I can plug -2 into it. I get 12 times -2 squared minus 6 times -2 minus 18. And we can compute what this is. 12 times 4 is 48, plus 12 minus 18. I don't really even care what the number is, but I see that it's positive. Right? So that means from minus infinity to -1, my derivative f prime is positive. If I plug in the second test number, right, if I want to know f prime of 0, that'll be 12 times 0 squared minus 6 times 0 minus 18, and that's minus 18, so that's a negative value. In other words, from -1 to 3 over 2, the derivative is negative. For the last test number, I plug 2 into the derivative. F prime of 2 equals 12 times 2 squared minus 6 times 2 minus 18. What's this? This is 12 times 4, so that's 48 again. minus 12, minus 18, and it's still positive. In other words, from 3/2 to infinity, the derivative f prime is positive. If you look at the increasing-decreasing test, when the first derivative is positive, the function itself is going up, right? So I draw an upward arrow to remind myself that f is increasing here. From minus 1 to 3/2, the function is going down or decreasing. From 3/2 to infinity, my function is increasing again. Okay, the arrows don't exactly tell me the shape, but they do tell me where the function is increasing and where it's decreasing. I think it's useful to summarize this in a sentence. In other words, f is increasing on what intervals? Minus infinity to -1 and 3/2 to infinity. Okay, the intervals corresponding to these upward pointing arrows are where the function is increasing. On the other hand, the function f is decreasing on that interval in the middle, from -1 to 3/2. Okay, when you write intervals of increase and decrease, you should write open intervals. You shouldn't use square brackets. The first derivative also helps me answer part B, where I was supposed to figure out if the function has any local maxes or local minimum values. In my little, schematic here, I can see a max and I can see a min because this is a high point and this is a low point. And so at x equals -1, I would expect f to have a local max. On the other hand, at x equals 3/2, my function f has a local min. Okay, the fact that that's true is due to the first derivative test, right? As I go from left to right past the critical number -1, my derivative changes from positive to negative. So I have a local max at -1. At the critical number 3/2, my derivative changes from negative to positive. So that corresponds to a local min. That's what the first derivative test tells me. Okay, in other words, the answer to part B is that we have a local min, or a local max, I guess we'll start with, at x equals -1. So that's where it occurs. And also the local maximum value is the value of the function at -1. Right, so if I want that actual value, I should plug the -1 into the original function. So that's 4 times -1 cubed, minus 3 times -1 squared, minus 18 times -1 plus 4. So -4 minus 3 plus 18 plus 4 looks like 15 is our local maximum value. For the local min, the function has a local min at x equals 3/2. To get the local minimum value, we plug 3/2 into the original function. I did this in my notes, I'm not going to do it for you, but you can check it. You should get minus 16.25. Okay, that's the local minimum value. Now, part C. With part C, I want to determine the intervals of concavity, figure out when the function is concave up or concave down. For concavity, we should look at the second derivative. To get the second derivative, I differentiate the first derivative. Okay, on the other board, we found that f prime of x is 12x squared minus 6x minus 18. So I differentiate that. First derivative to get the second derivative, in other words, I get 24x minus 6. The concavity test tells me to figure out where f double prime is positive. Right? F double prime being positive means that f is concave up. The second derivative being negative tells me that f is concave down. To figure out where the second derivative is positive and negative, we do basically what we just did for the first derivative. In other words, we should first figure out where the second derivative equals 0, and then we'll pick some test points on a number line. So we took the second derivative, 24x minus 6, we set it equal to 0, and then we solve for x. In other words, 24x equals 6, and then x equals 6 over 24, which reduces to 1 over 4. All right, that 1 over 4, I put on a number line this time for f double prime. This single number breaks the real line into two subintervals. And just like before, I picked test numbers for these subintervals. A number less than 1/4 is x equals 0. That's a nice one to use. A number greater than 1/4 is x equals 1. That one is also easy to plug in. For concavity this time, for this number line, it's a second derivative. So I want to plug these test numbers into f double prime, because I'm trying to figure out if f double prime is positive or negative. So first of all, f double prime of 0 is 24 times 0 minus 6. That's negative 6, that's negative. Right, so from minus infinity to 1/4, f double prime is negative. On the other hand, f double prime of 1 is 24 times 1 minus 6, so that's 18, and that's positive. From 1/4 to infinity, f double prime is positive. The sign of the second derivative tells me about the concavity of the original function. Right? When f double prime is negative, the function is concave down. When f double prime is positive, the function is concave up. I'm going to summarize again in a sentence to help me keep the information clear. F is concave down on an interval, minus infinity, comma 1/4. F is concave up on the other interval here, 1/4 to infinity. At a point where the concavity changes, at 1/4 in other words, as long as the function is continuous there, you have what's called an inflection point. And so the coordinates of the inflection point are 1/4 and then f of 1/4. All right, the inflection point is a point on the original function. So to get the corresponding y value for the inflection point, I should plug this x, where the concavity changes, into the original function. And in my notes, I computed this. In this example, there's a inflection point at the point 1/4, comma, -5/8.